Thank you all for being here this afternoon. Today I'm going to talk about a relatively unconventional electrochemical imaging method, which is based on the use of fluorescence. And we're hoping this might be helpful for looking at single cells or network of a lot of cells. In our mind, at least, electrochemical imaging has become increasingly important. Here I want to define a little bit about electrochemical imaging. This is different sort of than compared to the regular optical or scanning electrochemical scanning electron imaging, because the goal right here is to look at electrochemical reactivity and detecting changes over redox species. And so here I give you two examples to show that this really is becoming important. One example is neurocommunication in the brain, and the other one is electrocatalyst screening. We all know neuron in the brain is a really complicated system with hundreds of billions of neurons and talking to each other on a very quick speed. And in order to look at the brain communication, electrochemical imaging is a beautiful tool that we all learn a lot from Mark and Andy about. And so when we look at electrochemical imaging, here's what we want. First of all, we want high spatial and temporal resolutions. And especially when we look at neurocommunication system, we need spatial resolution on the order of microns or less, and temporal resolution is on the order of milliseconds or below. And we need high detection sensitivity. This is talking about detecting molecules down to hundreds or thousands of molecules. So we need high detection sensitivity. And we also need to be able to simultaneously monitor a large area. Right? If we want to look at a rat brain, this area that we're talking about is probably on the order of centimeters. We know there are several imaging methods that we can choose from, one of which is the scanning electrochemical microscopy, SEAC, which Bard Group has contributed a lot and pioneered this field since 1991. Here what we have is a ultra microelectrode scanning on top of a substrate that we're interested, and we can collect electrochemical responses from different areas from scanning this microelectrode. This SEAC method has all those advantages, but a challenge for this is it is not easy to look at highly dynamic systems, right, over a large area because there's only one electrode being scanned. The alternative way of doing this is use the electrochemical arrays. Here is a picture of a 10 by 10 100 electrodes array. And with this electrochemical array, what you can have is you can have high spatial temporal resolutions and relatively high detection sensitivity, and you can also do simultaneous monitoring of many different spots. However, it is becoming very technically challenging if you want to do a large array like this, or even greater than this number. So in our group, we have started to propose a new method of doing electrochemical imaging. And this is the picture of the whole method. What we have here is a bipolar electrode that is embedded into an insulating material. This is a membrane, which has a single electrode right here connecting to a top compartment and a bottom compartment. What we have is we have our analyte molecule of interest right here sitting on the top, and at the bottom compartment we have some molecules which we can reduce and become active fluorescent. So we can use optical microscopy to monitor the generation of the fluorophore. What we only need here is to apply a little voltage right here on the order of 1 volt, and to couple those oxidation reaction and the reduction reaction. So there are several different interesting features about this methodology. First of all, it is based on optical readout. And specifically, we use fluorescence So this can offer us high sensitivity, detection sensitivity. If we can do well, we can really go down to single molecule sensitivity. And it also utilizes a bipolar electrode to couple to couple two reactions. And third of all, if we expand this mechanism, we can do many electrodes in the same membrane. So that will give us the ability to image a lot of different areas to use the electrochemical array. So here what I want to focus on today is I want to focus on a few different things. First of all, I want to talk about electrochemical coupling on a bipolar electrode like this, because this is the core of this method. And then I'm going to talk about this reaction, the fluorogenic reaction of the reporter that we use, which is resazurin. And then after that, I'm going to demonstrate this method and then give you a couple examples to show the application of this method to look at diffusion of redox molecules and to look at electrocatalysis. And at the end of the talk, I want to discuss the spatial resolution of this imaging method and whether or not we can go to down to the nanoscale with spatial resolution. So while we are interested in bipolar electrochemical coupling, this goes back to my postdoc experience in Andy's lab, where I learned a lot about making those carbon fiber electrodes. This is a picture I borrowed from the venting group. Here what we have is a carbon fiber electrode sealed in a little micropipette tip. And so there are a lot of advantages of using carbon fiber electrodes, including low cost and easy fabrication, and fast response, and very small and very stable. At the early days in the 80s, since Mark developed this, people have been using metallic conductive materials like silver or carbon materials to make direct contact with a silver wire put into the backside of the carbon fiber electrode. So this basically is a two-electrode system where you can do neurochemical studies. And later on, people find you can do exactly the same thing by putting an electrolyte solution, for example, 3 molar KCl solution, and you can still have pretty good electroconductivity. And since the day that I was in Andy's group, I had this puzzle, and I could not understand what happens to give this electrocontinuity in this type of configuration. Later on, when I read about the bipolar electrochemistry literature, mainly published by the Crookes group, this is a picture of a bipolar electrode that I borrowed from Crookes' paper in 2009, which shows a bipolar electrode right here sitting inside a micro channel connecting the left side and right side, 2 compartments. And if you apply a voltage between here and here on the order of 10 volts or 80 volts, between 10 to 80 volts, depending on the scale of this microchannel, you can polarize and you can couple 2 reactions at the left side and the right side on the same micro gold electrode here. And so you can couple 2 reactions together. This really gives us some good idea about why this is happening. So based on the understanding of the bipolar literature, we propose that a carbon fiber electrode is really a closed bipolar electrode. This is the major difference between here and here is there's no ionic flow between the inner and outer solution. Okay? There's only electron flow between this end and that end. So what happens is when we have dopamine molecule sitting outside, we can oxidize it, and electrons will flow from here to here. And where you have a little bit of oxygen in the solution, oxygen will be reduced, and oxygen will be reduced. So couple those 2 reactions, and then we can finish up the circuit. This is what we propose that how carbon fiber electrode works. Now, as I mentioned, we really need to understand the bipolar coupling in a fluorescence experiment. So what we can do at first is we can look at a ultramicro electrode in a 2-electrode system. This is a system that everybody understands. So we have a working electrode, we have a reference electrode, and there's ionic flow between the two, and the electrochemical response is pretty much limited by what's happening on the working electrode by this equation for a disk electrode. And here I can draw the potential profile for this electrochemical cell, where this is reference electrode, this is a working electrode, and I can move up and down of this potential on the working electrode to make it an anodic or a cathodic pole. And here is the sigmoidal shaped voltammogram that happens on this working microelectrode, and so we can pretty much understand that. When it comes to a bipolar electrode, we have 1 and 2. We have 2 microelectrodes connecting in series. There's only an electron flow between this electrode and that electrode. And there's also ionic flow between here and here, between here and here. So now if we draw the same similar potential profile for this electrochemical cell, we have one reference electrode, we have another reference electrode. They're both non-polarizable electrodes, and so we can move their potential up and down and apply the voltage bias between here and here. So the voltage bias will all be dropped on between this membrane, so right on this bipolar electrode. And so we can qualitatively understand, if we drop this reaction, the total Faraday response must be limited by whichever has the smaller current flow on those 2 electrodes. And the amount of voltage that we need to drive right here must be related to the 2 formal potentials of those 2 reactions. Okay, so we can design several easy experiments to prove that. First experiment, we can have an electrode where we have a lot of redox molecules like ferricyanide, 5 millimolar ferricyanide, and we design this as an access pole because it has more current, access current on here, limiting current on here. And in this limiting pole, we put X millimolar ferricin. Okay, if we change the concentration of ferricin in this limiting pole, we can watch the limiting current goes up linearly with the concentration of ferricin. Here is at the beginning, we increase the concentration of ferricin, the total current goes up linearly with concentration of ferricin right here. And then it plateaus to a constant value. What happens is at this about 1 to 2 millimolar, about 2 millimolar right here, you saturate the current that's the maximum amount of current that can flow right here. So this pole becomes the access pole, and this becomes the limiting pole. Okay. And let me go back. For those of you who study ferrocene oxidation, you know ferrocene oxidation happens at about 400, 500 millivolts versus silver chloride electrode, and this reduction reaction happens at about 0.36 volts, 35 volts, and the difference of those 2 form potentials should be around 0.1, 0.05 volts, and so this is really where the amount of voltage they need to apply and the UN half of this overall current voltage response. And we can design another experiment to further prove that. What we did is we can put 500 micromolar ferrocene in this limiting pole, and we keep changing the species in the access pole, the species O. So here are 3 examples. By using oxygen, ruthenium hexamine, or ferricyanide, all right, we know exactly what their form potentials are, 0.36, 0.1, and minus 0.13. We can take the difference and we can verify that's really what's happening right here. Okay? So the take-home message here is the electrochemical response of the overall bipolar electrode happens at the potential difference of the anodic pole and the cathodic pole. And there's also a concentration dependence. That's something that we later on figured out. And here I want to show you one example where we keep the concentration of ferrocene at constant 50 micromolar. This is a very small concentration. And we change the concentration of ferricyanide at this access pole. Okay? So what we can see here is from 0, when we have 0 ferricyanide, there's something else, probably oxygen coupling to the oxidation of ferrocene. So we can ignore this one for now. And if we have a little bit of ferricyanide, this U1/2 is right here. And when we increase the concentration of ferricyanide, this U1/2 shifts negatively from here to here. So it turns out, as you have more and more redox molecules in the access pole, this CV curve becomes more and more reversible. Okay? At least from looking, it becomes more and more reversible. And so the typical method for here is a higher Faraday current on the access pole facilitates a more reversible looking CV from the bipolar setup. So I put a reversible, not really reversible, because there has nothing to do with the reversibility of the two redox molecules. Both molecules are reversible molecules. Okay? The change of the shape here is all because the coupling, the current coupling between the two redox molecules. And so now let's look at how we can better understand the bipolar electrochemical coupling on this electrode. What we have here is we have two ultramicro electrodes coupled together. Okay? And what we know from the beginning is we know the total voltage applied across this membrane is the voltage difference on this anodic pole and this cathodic pole. So this is your total voltage. And the Faraday current flowing on this pole is the opposite of the current on this pole. So that's some basic information we have. For each of the two poles, we know we have a sigmoidal shaped voltammogram on those two poles if we did separately. And we can understand this cyclic voltammogram by writing out the equation that we learned from the textbook. Okay? So the applied voltage here is a function of it's a log function of the current, and so that's what we know from the textbook. And we can do the same thing for both poles, and we can plug that two equations in this formula. What we have is this overall applied voltage is a function of the current here. Is a little more complicated function, and this is the difference of the two formal potentials. Right? This is the current that's generated over current. Here is the limiting current on the anodic pole. This is the limiting current on the cathodic pole. Okay? And we can figure out the U1/2 of the overall response. The U1/2 is just the overall difference of the formal potentials minus a log function of the ratio between the cathodic pole and the anodic pole. Okay? So that's why when you change your current on the cathodic pole, keeping the other one, this ratio, when we change this ratio, the U1/2 changes negatively. Right? When you increase this ratio, this U1/2 changes negatively. And we can put numbers into the equation that we just got, and we can simulate the overall bipolar response. Here's what happens when we systematically change the ratio of the two limiting currents from 1 to 100. Here is the 1, here is correspond to 100. So you get a systematic shift on the voltage axis. And we can do the experiment to prove that. Here is changing to 1 to 100. So there's a similar negative shift. And so what we have learned so far is we can use a bipolar electrode to couple two reactions, and the total Faraday current will be limited by one of the two poles, the limiting pole. And the position of the CV is going to be the difference in the formal potentials. And it's also strongly related to the reversibility and the limiting current ratio of the two poles. All right, let me tell you a little bit about the Faraday reaction. Now, after understanding those two coupling reactions, let's talk about the reported reaction. Okay? So for reported reaction, what we would like to have is we would like to have a fast redox reaction, fast electron transfer kinetics. We like to have high fluorescence quantum yield once this is generated. We want to have a higher quantum yield to better detect it. And we want to have a high contrast between this product and the substrate. We want this molecule to be completely non-fluorescent. And we want to have less interference from other redox species. If you have oxygen in the same solution, oxygen can also be reduced. And that will interfere with your overall detection scheme. Okay? So the reaction, the reported reaction that we are specifically interested is this reduction of resazurin by a 2-electron, 2-proton process, this is a non-fluorescent molecule. This becomes highly fluorescent. Quantum yield for this resolution molecule is 0.95 or it's more than 0.95. So it's a very good molecule. Of course, it can be further reduced by another 2-electron process, becoming a non-fluorescent molecule. And so we've done some preliminary studies of this reaction on 3 different electrodes, carbon, gold, and platinum. Overall, we have the best response on carbon electrode. This is the black curve is the CV response on the carbon electrode. And the red one is gold electrode, and the blue one is the platinum electrode. As you can see, the carbon electrode gives us the smallest over potential, and it has this 1 and 2 consecutive reduction reactions, and this is the one oxidation reaction. And here is the simultaneously measured fluorescent signal. This black curve again corresponds to what happens on the carbon electrode. So as you can see, this happens at the smallest voltage, right, around minus 0.4 volts, and correspond to this wave right here. Okay, and gold and carbon, they have much more overpotentials. And so what we find from this study is reduction of oxygen can really interfere with this detection scheme, and the carbon electrode gives the best response in terms of the less interference from oxygen and lowest voltage requirements. So let me demonstrate this detection with fluorescence. Here, what I have is an analyte solution containing some little bit 2.5 millimolar macromolar of ferrocene in this beaker. And here, another volume of solution sitting on top of a microscope. One electrode here, one electrode here. They're coupled together with a metal wire. And if we apply a little voltage scan from 0 to 1.4 volts, we can couple those two reactions. And here is at the beginning of the voltage scan. Here is as we increase the voltage, we start to generate fluorescent molecules. And this is when we scan it back, we have molecules diffuse all away from this electrode. Okay, so this is really exciting result. It shows that the proposed mechanism really worked. And more than that, we can, from the fluorescent signal, we can obtain fluorescent voltammogram, because we understand the total fluorescent is corresponding to the total number of fluorescent molecules. And that, if we use Faraday's law, we can take a time derivative of total fluorescent signal. That will give a way to represent the total current. The current should be proportional to the derivative of the fluorescent signal versus time. Here is one experiment result showing the simultaneous recorded electrochemical current, which is the red curve here, and the black curve right here is the time derivative of the fluorescent total count. Okay, so there's a good correlation between the two voltammograms. This one is the two-electrode system. As you can see, there's a big change between here bipolar and this two-electrode response. This is all due to the coupling, making it kind of looking like a slower response. One of the interesting features about fluorescence is there's no capacitance charging in fluorescence detection because in order to generate fluorescence signal, we have to have electrons to come across this interface. And the double layer charging, the capacitive charging, there's no electron transfer between this this interface. Okay, so here's the easy example to show you for a regular electrochemical response. There's a lot of capacitive charging hysteresis between the forward scan and the backward scan. Okay, if you take out the fluorescence cyclic voltammogram, this capacitive charging is not there. So let me discuss now how we can use this scheme to do electrochemical imaging. All right. So this can be easily done by integrating a lot of electrodes in the same membrane. So this is a diagram showing a lot of parallel electrodes in the same insulating membrane. On top of the membrane, we have redox analyte molecules. At the bottom, we have a lot of reporter molecules. What we need is a small voltage that's about 1 volt or below to drive those two reactions. Okay? And what you only need is a CCD camera to look at the signal, and you can watch all those electrodes simultaneously. So at the proof of concept experiment, I can put some photoresist to cover some of the electrodes and make a pattern out of this electrode array and see if we can image the pattern. Here is what my students did. They put on photoresist, and they made a pattern of a Husky, and here is the same pattern being imaged with fluorescence down here. Okay? And the scale bar here is about 100 microns. So this gives you some information about the spatial resolution. We can do some more interesting studies with this technique. We can place a micropipette, which has some analyte molecules. We can puff them out and image the whole mass transport process with the same setup. And what we have here is a similar carbon fiber electrode array, which from here to here, about 300 micron diameter, and has about 1,000 electrodes in this array. The thickness of this electrode array is about 100 microns. And here is a composite image showing 4 experiments. All right, each one of the spots showing a different experiment where this pipette is positioned right here, 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 and there. Okay, clearly you can see molecules are being imaged with fluorescence, and we can record the whole video to show the whole diffusion process when molecules coming out from at this time, and then there's more molecules coming out, more molecules, and more molecules coming out at the from beginning to the end. So this is the whole diffusion process being imaged by fluorescence, and this is the area of the electrode. Clearly, you can see there are some diffusion spreading out of the fluorescent molecules. So this is one of the challenges that we have to gain higher spatial resolutions, which I'm going to talk about. Another example that's even more useful is to look at electrocatalyst. Here what I have is I have the same carbon fiber array. On top of the carbon fiber, we put on platinum particles. They are good catalysts for a lot of reactions, for example, for the oxidation of hydrogen peroxide, whereas carbon surface is kind of inert for this reaction. Okay? So here's what we did. We put on 5 platinum bars. Those are platinum nanoparticles deposited on carbon fiber arrays. This is the blow up of platinum-coated carbon fiber. And here is what happens when we image this reaction of the oxidation of hydrogen peroxide. Of course, you can see there are more fluorescent signal on those platinum areas than the rest of the carbon. Okay? We can do a control experiment where we use a different molecule. This is a ferrocene-methanol molecule. This molecule is out-of-sphere molecule, which means it does pretty much the same reaction kinetics on platinum and carbon. So this is what happens. You see everywhere in this electrode array lights up with almost no difference. Right? We can do electrochemical cyclic voltammetry. We can prove there is more oxidation current on platinum than on carbon, whereas there is almost the same current on those two materials for ferrocene methanol. Now, what about spatial resolution? So, because this is an optical fluorescent-based imaging method, our spatial resolution limit has to be the optical limitation, which is roughly the lambda, which is the wavelength that you're working with, divided by 2 times the numerical aperture of the optical objective. But we have more challenges. We have redox generated on the electrode, and redox molecules want to diffuse, right? And they diffuse pretty quickly. If we calculate how much distance to diffuse for a molecule that I just mentioned, resazurin molecules, the diffusion coefficient is around 0.5 times 10 to the minus 5th centimeter square per second. So if you waited 1 second, the distance the molecules can diffuse is around 30 microns. And so even if you have a 1 nanometer electrode, the diffusion will give you a spatial resolution on the order of 20-30 microns. So you won't get a very good spatial resolution if you have this diffusion problem. Another technique we thought about is to rely on ECL, generated chemiluminescence. ECL use a different scheme where 2 co-reactants, ruthenium bipyridine and trace propylamine, they will be oxidized on this electrode, and then they will meet somewhere near to the electrode, and when they react, they can emit photons. Okay, this will give you a little better spatial resolution, but not too much. Here is one example. We have a 500 nanometer electrode, and here is the fluorescent image. We have a 5 micron scale bar, so you can see the type of spatial resolution we have is on the order of 5 to 10 microns for this 500 nanometer electrode. If we did the same thing with ECL, we get a increase of the spatial resolution about 1 or 2, a factor of 2, but not too much. We designed microelectrode arrays. Each one electrode has about 2 microns in diameter and about 6 microns center to center distance. And we do the same resazurin fluorescence, and I can show you pretty quickly whether or not we can image those electrodes. Here's the image, the video we have. So you can see we don't have a lot of spatial resolution, but we can really see the individual spots. But if we move to a smaller array with 1 micron size electrode and 4 micron electrode distance, we can't resolve at all with fluorescence. So this is giving information about the spatial resolution. We have about anywhere between 3 to 5 micron spatial resolution with current settings. We can do much better with ECL. Here is the ECL response. We can clearly resolve all those spots with ECL. So let me summarize. Overall, I have shown that we are proposing a new mechanism for electrolyte filled carbon fiber electrodes as close bipolar electrodes. And we have proposed a fluorescent-based electrochemical imaging methodology, which based on the use of an array of bipolar electrodes and the use of fluorescence to report electrochemical signal simultaneously. And our current research is focused on obtaining higher resolution in electrochemical imaging by taking consideration of the diffusion, and also we're working on single molecule sensitivity by using several different optical methodologies. And using this methodology, we want to study catalytic systems and biological systems. With that, I want to thank my group, especially Josh Grett, who contributed most to this work, and Steve Percival and Zhang, and another Steve Oya also contribute a lot to this work. And I want to thank NSF for supporting this work. I also want to thank all of you for your attention.
Thank you, Bo. I think we have time for a quick question. Rick?
I'm reacting to your comment that you don't see charging current. Because charging current is still current, so you can do redox. Maybe what you mean, and what I now understand, is that charging current is transient, whereas your fluorescent signal is over a period of time.
What I really mean is charging current does not contribute to the optical signal that you get, because you have to rely on electrons to pass the interface to generate a fluorophore.
I'll accept that in a steady state. But Al Bard, for example, had a paper a long time ago using a large area of silica as his counter-electrode and a small electrode up here. So he used the capacitance of this side to drive a microelectrode. So I would agree with you on the steady state. But I think transiently, charging current is still current. We can have a beer after this.
Yeah, let's do that. All right.
Thank you, Bo.